There we go. Hello and welcome back. We are today interpreting the loop and recur construct that we parsed last week. And this week I want to do a little bit of a special thing, namely I want to first of all show how to do it incorrectly and explain why that is incorrect and show why it's incorrect. And then do two different ways to implement it correctly. And then we can even check which one of them is faster. So I mentioned last time, that if we implement recur despite the name, I chose the name because the loop construct in the Clojure programming language uses the same thing. But recur should maybe be called iterate, because really it's just a loop, and no recursion in the sense that a stack frame is allocated should happen. And the reason for that is that a stack frame takes space in memory. But we're going to ignore that, and we're going to implement it by actually using recursion. And we're going to see that it kind of works, but that at some point the stack will overflow. So let's take a look back at what our data structure looked like. So we're using the same union element that we use for let. We're using that same thing for loop because it has the same components. It has a number of bindings, and then it has the body that we can see here. So these two are the bindings, A equals 100 and B equals 0. That's what the variables are initialized to when the loop runs for the first time. And then the body is this whole thing. And recur has a number of arguments, in this case 2. So what needs to happen is that when recur is executed, the loop is run again, set to these new values. So A would become A minus 1 and B would become B plus 1. So let's look at our interpreter and see where that comes in. So here we have let. And let's actually let's just copy it. I'm going to be a little lazy. Loop. And then, so right now we're doing exactly the same thing that we're doing for let. And then we have recur. And for recur again, we have a number, we have n arguments. So basically we need to evaluate these n arguments, and then we need to set, and well, not set. In this case, what we're going to do is we're going to just recursively evaluate the let loop, or the loop body, with these new values. Now, we can do this, right? So what we can do is we can say for int I equals 0, expr v dot recur dot n. So we're iterating over the n arguments, and we can evaluate them. Recur dot args of I. But then what do we do with them? And then after we've done that, we need to somehow get back to that loop that came from somewhere up the call chain, right? So we have to communicate to this recur down here that there's a loop up here that needs to be reiterated. And what we can do this in is we can just use the context. Actually, we don't have the context anymore when we're evaluating. And we don't have the environment. Well, we can't put it in the environment because the environment has no such thing. So we're going to do a very, very ugly thing. Namely, we're going to add an additional expression here, which we'll call innermost loop. So this is, for each expression, that's the loop that contains that expression, but is the innermost one that contains it. So in this case, it is this loop. And this loop, of course, has no containing loop, so it would be null. So that means that whenever we evaluate an expression, we're going to pass that in. Innermost loop. There's a lot of evaluating going on. So let, here it's still fine. The let doesn't change what the innermost loop is. However, when we are evaluating a loop, then when we're evaluating the body of the loop, what's the innermost loop here?
It is expert.
Yeah, it's the expression itself. Because that's the expression we're looking at. That's the loop. And it's the innermost loop for the body of the loop, right? So for this body, the innermost loop is this loop. So now, expr we're evaluating these expressions. We're also making an additional mistake, but we'll talk about that later. So one thing I can do is I can bind these to. Okay, but maybe I should explain. Now that I have the innermost loop, right? So the innermost loop is the loop that we need to recur here. And the first thing that I should do is maybe I should assert that the number of arguments that we get is the same as the number of arguments that the loop, or the number of bindings that the loop requires. If that is not the case, then it's the wrong loop, or it's not recurred correctly. So that's the first thing. Now, the second thing is I can actually bind these to the names that they belong. Namely, we know which names that they belong from the innermost loop. And I should actually pass null here. So this is another thing that we should talk about. So let's actually talk about this. We may have talked about it in the discussion in the very first video where we presented the Simplang programming language, but the recur expression can only occur in certain parts of, or in certain positions, let's call it. So for example, this could not be a recur expression, the if condition, right? It makes no sense to have a recur there because it's not the form of a loop. The if requires that the recur comes back. Does that make sense? But if we run it as a loop, then it will never come back because a loop is not recursive. So actually, formally, I think it's in the README. Recur. Recur is only legal within a loop and can only occur in a tail position. Okay, and then there's continuation, blah, blah, blah. So this is like the computer sciencey stuff. But in particular, a recur can never be the argument of an if, the argument to a function call, an operand to an operator, or on the right-hand side of a ladder loop. Right, so a recur cannot be in here, a recur cannot be in here, a recur cannot be like an argument, an operand to an operator, and it can't be here either as an argument to a recur or to a function call. Another way to think of this is, or let's say we were implementing this in a different programming language, like Java, right? Let's write this loop in Java, or in a Java-like, or whatever, C syntax, right? So we would initialize our loop with A equals 100, B equals 0, and then basically we would have a while true loop, right? A forever loop. And the loop body says this: if A equals 0, then, and because Simplang is a functional programming language, it doesn't say, it just says B, it doesn't use the return statement, but really this means that it returns the value B for the whole thing, right, for the whole loop. So in C, we would have to, if this were a function, in function returning an int, right? Then this would have to return. And this would also have to return. Except that what this actually does is it says new A equals A plus minus 1, new B equals B plus 1, and then it says A equals new A, B equals new B. I'm writing this in a weird way because it could be the case that for example, A could occur in the expression for B. And if we just said A equals the new value for A, then we would get the wrong value. So for example, it could say here A plus 1, right? And I would have to write here A plus 1. And if I just did this, then this would get the new value for A as opposed to the value that it was before.
And C, you don't have plus minus.
Oh, you have plus minus. You can say plus minus 1. I mean, minus 1 is just the number minus 1.
Oh, I didn't even know you could do that.
What, to write the number minus 1?
No, I guess, yeah, I guess I knew that.
And the space is optional. Like, you can still write this in C, right? A plus minus 1. But anyway, but now recur just means run the loop again, continue. Right? And so here it makes sense to have a recur because you are in a position where you could continue the loop because the alternative would be to return a value. Whereas you can't write continue in here, right? You can't say if A equals continue. It makes no sense. Right? Similarly, it makes no sense to do it in here. So that's what is meant by a tail position. It's very intuitive in a way if you understand it. So maybe the way to understand it is you can use it in a position where if you used a different expression, that expression would produce the value for the whole loop. Right? If I wrote 1, 2, 3 here, that would be the result of the whole loop. That's where I can write a recur for that loop. So coming back, that means, however, now that we passed in innermost loop here in a few places where we don't have to. So we said this thing here, it does technically have an innermost loop, namely this loop, but it's not a loop that you can recur from, right? So really, it doesn't make sense to pass an innermost loop here. However, the alternative and the consequent, they do. You can return from the consequent and from the alternative, which means that you can also recur from them. Operands, unary operators makes no sense. You can't say minus recur something, right? In the same sense that in C you can't write return minus continue. It doesn't even make any sense. Innermost loop. Same thing here. Doesn't make sense. Right operand doesn't make sense. So in the let, again, as long as we're evaluating the right-hand sides of the bindings, we can't recur. Right? Again, if you think about C, you can say something like, even if you're in a loop, you can say A equals continue. Or you can say A equals return 1, 2, 3 here. So these don't get an innermost loop. However, the body of the let does get an innermost loop. Now, same thing with the loop. The bindings don't get one. Also, this here is not an eval. It shouldn't be here. But now, the body of the loop itself gets expression as its innermost loop. Okay, so now we're back here. we need to recur into the innermost loop. So we are evaluating the, again, this is wrong. The arguments to the recur also don't get an innermost loop. We're evaluating these, then we're binding them. This is also wrong, but we're going to go with it for now. The reason why this is wrong is exactly the same reason why I introduced these new A and new B here. But I don't care for it that much right now because we have a more fundamental mistake that we're making. And I want to highlight that, and then we're going to go to how we can correct that weird thing. So we're making a new environment. Innermost loop, we're binding it to the name of the bindings from the innermost loop. This is not a thing. So now we have the new environment, and now we could evaluate the body of the innermost loop again with that new environment, right? So I could say evaluate innermost loop body, and what is its innermost loop? Its innermost loop is, that's a tricky question.
It's just null.
No, it's not null. It's the body of a loop. It has an innermost loop.
It's just the innermost loop.
Yeah, it's the innermost loop itself. Now we have a result. Well, we also need to do this thing. We're introducing new bindings. So at some point, we need to release them. So is this going to work?
Sort of.
Main.c parse eval.
I need to pass in.
Oh, yes. I need to pass in here null as the innermost loop. So let's see what happens. Too many arguments. Oh, yes, of course. We can also add additional asserts, namely, first of all, the innermost loop must not be null, right? And we can assert that the innermost loop, what is it, type equals x per loop. Okay, so let's, we have a loop in tests parser 1.8. Let's see, loop recur 1.sl. Well, that's not going to do much. That is an endless loop. Okay, so that's exactly the one that we had before. Let's think about what this loop does actually. So it sets A to 100 and it sets B to 0. Then it says if A equals 0, then it returns B. Otherwise, it recurs, decreasing A by 1 and increasing B with 1. So what is the result that we should get? 100, right? So it just counts down B, and for each 1 that it counts down A, it counts up B. I'm sorry, it counts down A, counts up B. So by that, we do actually get 100. Now, let's try the following. Interpreter 1.9, copy parser 1.8, loop recur 2 into interpreter 1.9, and make it 1000. What is it going to do?
The same thing, 1,000.
Maybe. I mean, yes, it will. Let's try 10,000.
What is Xile?
It's a little Emacs. Okay. Let's try 100,000. Oh, segmentation fault. What happened?
Stack Overflow?
Yeah. So what we can do is, you can look at this with GDB, and I'm gonna, oh no, this is the worst thing ever. Do you know how LDB works?
No.
Shit. I don't even know how to start it with a file. Let's see, maybe something happens. We really only need to get a backtrace, so yes.
Bad access.
Oh, did it say bad access? Okay, so I'm asking it for a backtrace. I hope it doesn't crash. Yeah, see. So this is what happens. Oh, wow, it actually prints the whole backtrace. So what happens is that, so you can see we have about 37,000 stack frames. So that's how far in it got. Because for every iteration of the loop, it needs to run eval expr for the body of the loop, which is the if, and then for the recur, and the recur again calls eval expr for the body of the loop, which is the if, and then it again goes into recur. So basically we have 2 calls, and as you can see, they're switching up here. It's like we stop in line, we have a call in line 152 and another in line 70. And they just recur and recur and recur until the stack just overflows. So let's actually look at lines 70 and 152 in interpreter.c, and we will see that those are the calls. So this is line 70, as you can see. It's the call to the alternative of the if expression that corresponds to this here. And then in 152, this is the evaluation of the loop of the let body, which is this whole thing of the loop body. Clearly, this is not good. This should not recur indefinitely. So the problem now that we have is that instead of going further down each time, we need to come back up again. So essentially, this thing here that runs the recur, or actually I should say this one. So this line 139, that's the first run through the loop. That's here. This is the first time the loop is evaluated. And from there on, it just goes down and down and down again. So what needs to happen is when we are here in line 152 and we want to recur, we actually need to come back up here, right? And then we can run recursively again, because we never go deeper than 2 levels. So how are we going to do that?
One way you do it is replace the result, or like the type of the result to be like a discriminated union of either an int or the new parameters that you're supposed to run this thing with.
Yes. So what Bate is saying that is that we should basically make eval expr return either an integer or the new values for the loop bindings. So a regular expression would just return an integer, and that would be the result. But if it's a recur expression, it would actually return to the caller saying, look, I've been recurred. If you're a loop, please run again with these new bindings. So that's the, well, the other one is also kind of straightforward in a way. But we're going to do this one first. And I've just been thinking about, so one way we can definitely do it is by making the result into, I don't want to make it into a union, because then I need to have another field that says which one it is, right? But I could, which doesn't save us much. But if we instead just make it a struct with 2 elements, it could be, the first element can be the integer and the second element can be maybe a pointer to the new environment.
Yeah.
And then if the environment is set, then that's the new environment that we need to run it with. Which might,
Then like freeing the environment, isn't that going to be a little messy? Like who frees the environment?
yeah, that might be a little bit messy. We'll think about that as we go along. I've been thinking about another possibility. So we have another problem. And maybe I can show that problem with another test case. Namely, I said that test interpreter 19, let's call it names.sl. Yes. Let's make a loop where a is 1 and b equals 0. Wait, do I want that? Sure, I don't care about b actually. And now I'm just going to think about doing the recur first. So what I want to do is I want to use a for both of these. So I could say a plus 1. And then for b, I could say a. But this would be an endless loop, which I don't want. I want the loop to terminate, and I want to terminate at the second iteration. How can I do that?
If B equals, or like double equals, I think it's gonna have to be like 4. Or,
4?
no, wait, please. No, it's
So
no,
so
I-
if this executes correctly, what should in the second iteration? So first time through, A is 1 and B is 0, right?
Yeah.
Second time through, what should the values of A and B be?
they should be 2 and 1.
Yes, 2 and 1, because since A is 1, this is 2, and this is 1.
But it's gonna be
Right.
2 and 2. So like
Yes, because we have a mistake.
If A equals 2,
Right.
then
So if A equals 2, then we're just going to return B. So if this executes correctly, again, what should this return?
1.
1. But let's try it out. Called it what? Names. What? What is the mistake that I made? T-type binary operator. Eh?
Gotta be that double equals somehow. No, it's fine.
That seems weird. Is it possible that I have a bug in the scanner? No. I mean, it's still possible, but that's
Wait,
pretty
it
much
says-
exactly the same code
It
as
says greater than first one. Can I see the error?
yeah, it's just saying
Yeah,
it's expecting a binary operator. But where is it? Oh, I'm an idiot. Never mind. Okay, we get 2. Our grammar right now is kind of fucked up because we don't have operator precedence. So the parentheses actually mean a binary operator is coming. And we have the extra parentheses because of the recur. And if I put extra parentheses in there, it expects a binary operator here. So anyway, so we get 2. That's wrong. The reason for that is that we evaluate when we're recurring, we evaluate the second element here in the context of, in the environment of the first one. Actually, that's pretty easy to fix because we have the old environment here. So we only need to use the old environment. And we can run it, and it gives the correct answer. There is one weird bug that we have, which is the following. Let's say, let's C equals 1, 2, 3. Okay. this will get really weird. In let C equals 4, 5, 6 in, and now I'm not passing A in, I'm passing C in. And we're returning C here, right? So the B really has no significance. B is just a dummy. Oh, never mind. I'm sorry. I'm passing. No, wait. I'm confused now. Yes, we're returning C. Okay. What should the result be?
4, 5, 6.
The result should be 4, 5, 6?
Actually, no. It should be 1, 2, 3.
Yeah. So this C is bound here, right? It must always be 1, 2, 3. It's not rebound anywhere here in the path from here to there. B should be 4, 5, 6, right? Because we're passing it in here as the value for B. But C is not. C should always be 1, 2, 3. See what happens. 4, 5, 6. Why does that happen?
Because you're taking the environment from the lead and passing it onto the recur.
Yeah.
And then that thing keeps on, and that recur passes that environment.
So what we did was we are extending the environment in which the recur is evaluated. We're extending it by giving new bindings to A and B. And we're using that extended environment to run the next iteration of the loop. And in that environment, C is 4, 5, 6. But it should be 1, 2, 3. Because the environment we should be extending is the environment of the loop body. Actually, not even the environment of the loop body. The environment of the loop is what we should be extending. Right?
So all should be NMOS. Actually, no.
So the problem is now we need to pass in two things. We need to pass in not only the loop, but also the old environment of the loop. Because those are two completely different things. The environment is dynamic. The loop is a static syntax tree, right? And we have the same problem when we return from the recur and we return outwards toward the loop. We also need to put the binding somewhere, right? What we could be doing is we could be allocating a completely empty, like an environment that doesn't extend any other environment, and then we could append it. The other way we could do it is we could dynamically allocate a thing, which I'm not a big, well, I mean, we're doing it anyway, whenever we extend an environment. So what should we do?
I think the easiest way to do this and like manage the environment would be to return the like a dynamic list or like an array of the parameters or an array of the bindings or the new bindings that you need to run the loop with. Because then freeing the environment, I'm still, I guess I haven't thought too much about it, but you have to know about the old environment. So you would also have to pass that to the loop if the recur returns, right? So you have to, if you modify the environment in the recur, I guess you can still, I guess you could still do that because you have the loop.
Okay, do we want to fix? I think we should fix this. And to do this, we need to pass in the old environment anyway. Right?
Right.
So let's do that. So what we need is also the loop env. And again, this will just be passed through loop env. And there's none here. None here. None here. There is also none here. But here again, it's the loop env. Did I do that in the if? Yes, I did. None here. And here, what is it? No, it's not in.
Old.
It's old.
Old.
So the environment that needs to be extended by recur is that environment, because that's the environment we extended when we did this, right? And here, same thing, nothing. Well, here, the environment that we need to extend is the loop env, right? And actually, what I need to do is old needs to be loop env because we also need to free that, right? So we free everything from loop env up to old, and loop env gets extended, well, no, all bullshit. The argument to recur is always evaluated in the current environment, right? But the environment that we're extending is the loop environment. Here we're extending the loop environment. And then when we're freeing everything from loop environment to old, because that's what we've allocated. And the environment in which we evaluate is also loop env. And the environment that we pass is also loop env. No, it's not loop env, it's old. It's the environment from outside the loop, right? Okay. Wow. Okay, again. environment t loop env. So that's the loop environment. And in main, I need to pass in null. All right. So let's go. 1 to 3. Hooray. Okay, so now we fixed both those bugs. We can actually check that we fixed the other one too. Namely, if I pass in B, and this should still be 1. Right?
Should be 4, 5, 6.
Oh, 0, I'm sorry.
0. Oh yeah.
Because we're just passing, B is never modified, right? Okay, but we still have the recursion problem, right? That hasn't gone away. So if we run loop recur, it's still going to segfault. But now, fortunately, we know which environment we need to extend. So all we need to do is instead of here, sorry. Instead of recursively evaluating here, we should do something like return please recur with the loop environment, right?
Yeah. So if you have a loop, and then within that loop, there's an if statement, and then this recurs in the consequent of the if statement. The if statement gets the please recur, and then that it would pass that onto the loop, which has the old loop environment, and it can okay.
Yeah, an if statement would just pass it on, right? But so the thing that we need now is we need a data structure. So let's call it int p result t. Actually, what I should do is I should just call this eval. This is an internal function, and I should have a public int64t eval expr, which doesn't take these bullshit arguments because the caller shouldn't need to know about that, shouldn't have to know about that, and it will return a get. What do we call it? Force result of eval env expr null null. And force result means assert that this is an integer result and give it to me. Right? So assert that it's not a loop recur, because a loop recur cannot be the outermost result. You can't just a function can't return a recur, right? The recur needs to be statically nested inside a loop. So let's in here make this type def struct int p result p, and what it's going to have is an int64i and an environment. Let's call it loop env. And By default, this is 0. This is null, in which case the integer is valid. So we're going to make ourselves a function that returns make int result. It's an int 64t and int t result t as equals I null. Return res, right? And we can do, we're only going to use it in one place, but whatever. Make recur result, which takes a loop end. And returns that, and then we have force. We have static. Actually, I should call it int result of int t interpreter result t. And we assert that result.loopEnv equals null, and we return result.I. Right? So the nice thing is that we get back the nice this thing, and all of that additional stuff is internal. So that's good. Now, however, we need to worry about where we return what. So if we return an integer, obviously we need to call make int result. Right? Same thing here. We're looking up, which cannot give us a recur, so it has to be an integer result. Now, this is interesting. The condition to an if must always be an integer, right? It can't be a recur. So we can actually force here. Oh, and also all eval expr will be replaced by eval. Nice. So furthermore, now here, the nice thing here, just as we said before, we don't have to do anything here. If the consequent of an if returns an integer, we just return the integer further up. And if it contains, if it does a recur, we also pass it up. Nothing, no code is needed. So that's pretty good. Here again, we need integers, so this must be make int result. And actually, here's another nice thing. No, it's even nicer because we can just call, look, it's really, really nice. We can put this here, not static, by the way. We put a forward declaration here. So that this guy knows about it. And now the awesome thing is, this here just becomes eval expr. And we don't have to pass these nulls anymore. And we don't have to force. Isn't that great? You're not as excited as I am? So same thing here, eval expr.
In the unary thing, you have to, don't you have to return?
Oh, yes, you're right. So here, of course, we do have to say make int result. minus operand make result. So that unfortunately you have to do. That's okay. Boolify int. I think boolify int could just return the int result. So what's the difference between? Oh, I see.
Not things.
And then where do I call bool to int? Is that also? Yes. So that also I can do int p result t. So I don't have to do it multiple times. If operand make int result eval expr return boolify int, don't have to do anything here. Need to do that. Eval expr. Okay, let. Here again, we can use eval expr. So that's the easy part. And well, actually, there's no hard parts because the let again just passes on whatever it's given. Right? If there's a recur inside a let, that just goes up to the innermost loop. Here, however, we need to be vigilant. Do we? We bind, and then, so now here, this is now the interesting part, because if we, p, we're freeing the old environment. No, we're not freeing the old, we're freeing the environment that we allocated. But now, here's the interesting part. If the result does not contain a loop environment, that means no recur has happened inside the loop, then we just return the result. Oh, yes, if it's null.
Actually, shouldn't it just be like, you can do this like in a while loop, while.
Yes, we're going to have a loop. But
otherwise,
let me first see what it looks like for one iteration, and then we'll do the loop. Otherwise, we do have the new loop environment in the result. So what we actually need to do is we need to, well, it's not that simple. We could say, we can say env equals result.loop_env. And then we evaluate again. But then again, we need to check whether what we got back is if what we got back is null, and actually we still need to free this. So can we do this in one loop? So we need to do while loop because we need to evaluate it at least once, right? So at least once we need to evaluate result. We need to free the environment, if the result is, if it has not recurred, then we can break the loop. Actually, it just becomes an endless loop. Break the loop if there was no recur, and if there was a recur, we set the new environment to the loop environment. And that's it. And then we return the result, because we can only get through here if we've broken, if we've braked here. Does that make sense?
Yeah.
So here we have the loop that drives the loop recur. So again, actually I
just
can
return the result in the break.
We could. I like it better this way. If for some reason we change the thing to do something at the end, then it's not going to break it. So again, let's think through this again. So the environment that comes from above is env, right? That's old. So old is the environment within which the whole loop expression will be evaluated. So that needs to be the old loop environment, basically. And we have just bound stuff on top of that environment, and we always free that. And we free it even if it came from the recur. That's the unfortunate thing with C. You need to do your own memory management. If the loop environment is null, we don't need to free anything, obviously, because whatever we freed here. Okay, so now the only thing really we need to do is we have a please recur, and it's called make recur result, and we give it the environment. And we don't need to free because the free happens here. The loop always frees the environment. And it doesn't make sense to do it, to free it here, because we haven't even evaluated the next iteration yet. Think that's going to work?
Mm-hmm.
Very optimistic of you. Yeah, we don't need that anymore. Result. Oh. Well, yes. So maybe we will return it here. Whatever. Result. So this should never happen. Right? This loop cannot come out here. Also, what did it say here? Oh, this needs to be eval expr. Unused variable old loop env. Ah, yes, because we don't free anything in here anymore. We only add to an environment. All right, look at that. 100,000 iterations. Do you want to try more? Are you satisfied that it works? Oh, let's try a little more. And it still works. Okay, good. So I wanted to do a second one. However, it's complicated. I just found out by thinking about it casually. So a different way to do this would be, most programming languages have a construct that actually allows jumping from an innermost stack frame to an outer stack frame. What is that?
Just going innermost to the
Like-
outermost.
Not from innermost to outermost, from the current stack frame to some stack frame that's further up.
Just go to the parent, like basically. I guess with C, they
Don't think about C. Think about C# or Java or Python or.
If you go up the syntax tree, so like if
Syntax tree? No, you're in a recursion somewhere. No syntax trees involved.
I'm in a, wait, what was the question again?
You're somewhere 10 levels deep in calling functions,
Mhm.
right? There's another way to come back other than just returning and returning and returning until you're back. Okay, what happens when you throw an exception?
You basically, whoever catches handles the. It basically goes back to the point where.
Yeah. So throw an exception can jump over stack frames, any number of stack frames. So what we could do, let's say if this were written in C# or Java or Python, we could just use a try catch here in the loop. And whenever we recur, we could throw an exception and make the exception contain the results of the recur. And we could catch it here and we would just be there no matter how deep we are. And we would always be at the right loop because the nesting of the catch automatically ensures that you get to the innermost one, not to, a higher one higher up. The problem with C in particular is that, first of all, C doesn't natively have a try and a catch. It does, however, have a facility called long jump. And long jump is really weird. So it's called set jump and long jump. Basically what you do is you can use the function set jump with a jump buffer, and the jump buffer is just a local variable. What it looks like is that, let's see, what does set jump return? Set jump call, they then returns the program executes as if the corresponding. It just returned the value specified by that. Yeah. So what you do is, let's write it in Scratch. You would say, I have a jump buff. They call it jump buff, my buff, right? And then you say, if set jump of jump buff, my buff, equals 0, do whatever you were going to do, right? This is as if the code, this is what happens when your code runs the first time, right? However, set jump will return a value other than 0 if, let's say my func, if my func somewhere called long jump. Long jump. And it also, by the way, it also needs it also needs to jump up. It also needs my buff. Let's say this is whatever, the caller, and he has int result equals set jump. So if the result is 0, that's the first time the code runs. However, here, in here, result will be 1, 2, 3. Because my func has long jumped back. So you can think of this as, this is the try, and this is the catch. And what you get back is that number. You can pass an integer. And you can use that to implement exception handling in C. The problem is that we're using manual memory management, or manual. We have to manually deallocate environments and stuff. But if we just jump from here up to here, then all the intervening calls might have allocated environments that we don't deallocate. So we would have to have additional bookkeeping, either additional bookkeeping that makes sure that will be deallocated, or we would have to, in all the cases where we allocate stuff, we would have to also do the set jump. And in case we do have to have a recur, then we would have to deallocate and then long jump again. So it would be very, very complicated, basically. If you're using a garbage collected language, that would not be a problem. And also probably you have a nice try and catch. So you can totally do that. It's not a lot of overhead. Well, overhead. It's not a lot of code to write. The overhead is another question. The thing is that most languages treat exception handling, or not exception handling, I should say, most implementations of programming languages treat throwing in an exception as something that is an exceptional thing. So they don't optimize it to be fast. So it could very well be that this is actually, depending on which programming language implementation you're using, that this way to do it, the one that we're using here, it might be much faster than throwing exceptions, despite being a little bit wordier to write. All right. That was a long one. Questions?
Yes, in the test, you should probably have it out.
Oh yes, we should at least write a few tests. Yeah. I should move the names to names 1 and copy names 1 to names 2.sl. So names 1 is which one? Names 1 is the one that returns B, right? So this returns B, and it should be 1. And names 2, we're going to make it return C.
It should be 0, right? Yeah, with B, it should be 0. The first one, names 1.
Oh, it should return 0.
Yeah.
Yes. Let's just make sure that it does. Names 1 returns 0. Names 2 returns 1, 2, 3.
Names.
So let's just names 1.out, names 2.out, and then we also have loop recur. Can we make a what? Oh, I'm stupid. Parser 1.8, loop recur 2,
Yeah,
.sl. I overrode. No, I overrode my own file. How many did we put in? 100,000? It's gonna be out, not SL. It's 100,000. So we should at least have one example where we have a nested loop, so a loop inside a loop. I think in the example somewhere we have it. We have the 8 queens. There's a loop. Really? Do we have a div in here? No. I wrote is prime. Prime, next prime. Feeding zeros. Oh wow. There's no nested loops. Huh. Can you come up with a nested loop?
Yeah.
Okay.
We're just gonna
Tell it to me.
just gonna like do the area of an integer rectangle,
The area of an integer rectangle.
but just doing loop. So basically, you just go through, the inner loop goes this way and horizontally, and you recur. You could basically do that thing where you're decrementing from one and incrementing from the other, and then in the inner loop, and in the outer loop, we'll do something like
That's just busy work.
It's just definitely busy work, but it's
Well, if we're gonna do busy work, let's do something that's easy to verify. Like
that is easy to verify. It's the
no, let's just
area of a rectangle of 2 numbers.
What do you mean the rectangle of 2 numbers?
Let me start writing this.
Okay.
I might. We'll just say x equals. Let me think about this. I'm gonna do the inner one first. X is equal to. We have to bind these. No, we don't have to do that. We'll say 6 and let's just wait, what?
Never mind.
And y equals 0. If y or x equals 0,
That has to be a then.
yeah, then
Oh wait, are we just multiplying?
yeah.
Oh, why don't you just say multiplying?
I told you it's the area. How else do you get the?
Okay, so you're doing multiplying by incrementing. Okay,
Yeah.
okay. I was going to do exponentiation by addition, but it's the same thing.
Yeah.
Yeah. Okay.
Recur with x plus minus 1.
But you need double parentheses around it.
Yeah. And then y plus 1.
Yeah. Okay.
Now.
That's
Okay.
the stupidest. That's the stupidest busy work
Okay.
ever.
So
Because
now,
literally we're doing what? There's one instruction in the CPU for it.
Yeah.
But never mind.
Loop.
Let's use
so-
I and J or something.
Okay. I is equal to.
Yeah, maybe A and B. You're right. A and B.
I is equal to 5.
Yeah.
And is equal to 0. And, so if A is equal to 0, then I'm going to say B,
Sure.
else B plus, oh no, recur,
Mhm.
recur with B, or sorry, A plus minus 5, or plus minus 1,
Okay.
then B plus, and then you got this loop.
Yeah, B plus the whole loop.
Yeah. And then
You
I
need
need
to
the
do
double. Yeah. And that should work. I guess I could say we could indent this, but
that.
all right, that should be 30.
Yeah, that should be 30. Yeah. Okay, let's try that. And that's a loop. Boom!
Huh?
Yeah, we just calculated 5 times 6 in the most complicated way imaginable. But it's nested loops and they work. So note, of course, that now for this recur, the innermost loop is this loop. Note the nice thing about Simplang is, other than in C, you can just write a whole loop inside an expression, and it will also just work. All right, let's put that into nested loop and just make sure that not all the files correct. Wait, what? Oh. Interpreter 1.9. Yep. All right, we're done. So let's look at the next assignment. Okay, that's going to be another tough one. So, well, the nice thing about the next assignment is that it's just a change in the parser, and ideally, it shouldn't even require a change in the interpreter to work. But the change in the parser is to implement operator precedence. So up until now, we always had the problem that when you wanted to write a complex arithmetic expression, because of this grammar rule, the binary operator, you always had to surround by parentheses, like here or here, no matter whether the precedence of the operator requires it or not. So if you want to do 1 plus 2 plus 3, you have to write either 1 plus 2 plus 3 like that, or you have to write it like that. But you have to parenthesize. But what we want is, we want to write 1 plus 2 plus 3 just like that. And we want to be able to write 1 plus 2 times 3 so that it works out as if it had been parenthesized like that. Let's go back to this. So the change in the grammar is that we now distinguish between primary expressions and like the top level expression thing. And these expressions are just composed of primaries separated by binary operators. And the primaries are everything that you can parse easily without having to do any precedence overloading. And that includes, obviously, parenthesized expressions. And it also includes all the control constructs and all the integers and identifiers and so on. So basically, the primary is everything that we had before, including this little thing, but minus the binary operators. So that's easy to do. And then what the expression does is it parses one primary, and then it looks at the look ahead and says, do we have another binary operator? And if yes, then there's another primary. And if there's another binary operator, then there's another primary until we run out of binary operators. But then the problem is, how do you figure out which one to give precedence to, and how to put the parse tree together? So there's one algorithm that I linked to called the shunting yard algorithm, which is a standard algorithm that you can use. And one of the things that it's optimized for is that it does the precedence overloading as you are parsing. Like, as you are consuming these primaries, it decides, do I have to put it into a tree, or do I keep it and put it into a tree later because a higher level operator might be coming? But there's a much simpler way to do this, which, did you use the simple way?
No, I did the shunting.
Oh, you did the shunting yard too? So I'm going to tell you the simple way. If you don't want to know the simple way, you can turn off now and figure it out yourself, because it's really pretty simple. But the simple way is you just read the primaries. So the one here is a primary, right? And then there's a binary operator, and then there's another primary, and then there's another binary operator, and then there's another primary. And you just gather these together until you have basically a list that contains primaries and in between binary operators. And now all you do is you go from highest operator precedence to lowest operator precedence. For each operator precedence, so let's say we're looking at the precedence of the multiply operator, you just go through your list and go like, you look at one operator after the other from left to right, and let's say we have another one here, times 3 times 4. And if that operator is of that precedence, you make a new expression out of it, out of the whole thing, by basically parenthesizing it. So this becomes its own thing now. But this is now one entry in the list, right? It becomes put together. And thereby you remove it from the list. And then you go on and, we have another operator of this precedence, so I'm going to put that one together too. Sorry. Right? And now all of these have become one expression, and we're done with this operator precedence level. We go up to the next lower precedence, which is the plus. So for the plus, now there's only one operator left, and it's a plus. So we put these together, and we're done with the parenthesized expression, and that always works. Does that make sense? All right. Well then, good luck, and I'll talk to you next week. Bye.